Hi everyone. We're going to learn about trig identities today. Our first learning goal is to learn the difference between what an equation and an identity is. And then we're going to learn how to prove a trigonometric identity. This is the first time you're going to see them in grade 11, and then you'll do them kind of more challenging ones next year. An identity is an equation that is true for all values of the variable. So one side of the equation is another way of writing the other. That's how you can think of it. So some identities that we can, you may have seen before or not known they were identities, but they are. 5x plus 25 is equal to 5 times x plus 5. So the right side is just another way of writing the left side. Same, only it's been common factored. Same with x squared minus 4. Factoring it to get x plus 2 times x minus 2. Both sides are equal. They're just another way of writing it. Secant theta is the reciprocal of cos. So they mean exactly the same thing. Secant is 1 over cos theta. And then here's a identity that we used when we were simplifying rational expressions. A minus b is equal to negative b minus a. So identities, the other thing that's true of identities is that they're true for all values of the variables. So it doesn't matter what x is in this case. Both sides are always going to be equal. Same with this one. Same with doesn't matter what theta is. And then if you stick to a certain a and b, it would be the same on both sides for this as well. Whereas these are equations that aren't identities. X squared equals 3x plus 4. That's a quadratic equation. And if we rearranged it to get all the terms on one side, we could see that this one would be solvable by factoring. Which would mean this one's only true if either x is 4 or negative 1. Okay, so this is true no matter what value of x you choose. X can be any number and it's always true. This one is only true. X squared only equals 3x plus 4 if x is either 4 or negative 1. Okay, here's like a grade 9 equation. 2x plus 1 is only equal to 7 when x is equal to 3, only for x is equal to 3. So there's only one solution that works here. Another kind of grade 9 equation. This one's only true if, so you'd multiply both sides by 4 and then add 3. So if x is 23, 23 minus 3 is 20 divided by 4 is 5. So it only works when x is 23. And sine theta is negative 3 over 4 for angles between 0 and 360. We just learned that with the cast rule. We could find the two angles that would make this equation true. So it would only be true for two values. So identity is true for all values of the variable, always true, in other words. So always true. Always true, sorry, I wrote that here, always true. And non-identities, equations that are true for a certain number of values, okay, but not all values, so not always true. So some trig identities that we should already know, so some things that we should know are always true, are called the reciprocal identities. So these 6 here are called the reciprocal identities. So we should always know that sine can be written as 1 over cosecant, or cosecant can be written as 1 over sine. Cos could be written as 1 over secant, or secant can be written as 1 over cos. Tan can be written as 1 over cotan, and cotan can be written as 1 over tan. So those are our 6 reciprocal identities, and they come from how sine and cosecant are related, how cos and secant are related, they're reciprocals of each other, and how tan and cotan are related. They're reciprocals of each other. We're now going to, these 6 again, they're considered fundamental identities because they're just things we should know are true, we should have in our head, okay? We're going to prove some more fundamental identities here, and these ones are called the Pythagorean trigonometric identities. So they start with, we can see we have an angle just happens to be in the first quadrant, easiest one in standard position. But we know that r, x, and y are related using the Pythagorean theorem because it's a right angle triangle. And where the Pythagorean identities come from is first we decide that we can divide both sides by the same number, and we haven't changed the equation. So what we are going to do is divide both sides by r squared, which is the same as dividing each term on each side by r squared. Okay, which gives us r squared divided by r squared is 1 here. Here we have x squared over r squared, which using exponent rules, we can write as x over r all squared. Okay, and we could write y squared over r squared as y over r all squared. But based on last week, we know that if we're looking at this diagram here, that the cosine of angle theta is equal to x over r. So I can replace x over r with the cosine of angle theta. That's squared. And from this diagram, we know that the sine of theta is equal to y over r. So we can change y over r squared to sine of theta squared. And that's our identity. The only thing is that there's a short form of writing cos theta with brackets all squared, and that's to write it as cos with the squared between the s of cos and the theta. So that really means cos theta squared, but we say cos squared theta. And then we could rewrite this one as sine squared theta. And then really when you see this one in a textbook, they always write it like this: sine squared theta plus cos squared theta equals 1. And that's the most famous trig identity. If someone's going to remember one trig identity from high school or in their life, it's going to be that sine squared theta plus cos squared theta equals 1. So that is the most famous trig identity, most common, okay? And it should be a fundamental one. So everyone remembers sine squared theta plus cos squared theta always equals 1. Okay, so there's 2 other Pythagorean identities that are constructed in the same way. So we're going to start off again with r squared equals x squared plus y squared. But this time we're going to choose to divide everything by x squared, which is the same, or both sides by x squared, which is the same as dividing every term by x squared. And we know we can write r squared over x squared as r over x squared. X squared over x squared is 1. And y squared over x squared we can write as y over x all squared. And then back to our picture here, we know that if cos theta is x over r, then sec theta would be r over x. So I could write this as sec squared theta is 1 plus, and then we know that it's the tangent of theta, that's y over x. So sec squared theta is 1 plus tan squared theta. Okay, so that is the second Pythagorean identity. And then hopefully you could imagine how we would go about getting the third one. So again, we're going to start with r squared equals x squared plus y squared, but now we're going to divide everything by y squared this time, or both sides. And then we can write r squared over y squared as r over y all squared. X over y, sorry, x squared over y squared can be written as x over y all squared plus 1. And if sine is y over r, we know that then cosecant would be r over y. Oops, forgot to put the squared. And if tan is y over x, then cotan is x over y, so cotan squared theta plus 1. And there's our last Pythagorean identity. So we've gone from these 6 we should know, the reciprocal identities we should just know, okay, how they're related. And now we've got 3 new Pythagorean identities. Okay, so these are the Pythagorean identities. Write them all down in one place here. So sine squared theta plus cos squared theta equals 1. 1 plus tan squared theta equals sec squared theta. And 1 plus cotan squared theta is equal to cosecant squared theta. So those are our 3 Pythagorean identities. Okay, with the most famous trig identity being that sine squared theta plus cos squared theta equals 1. All right. So there's 2 other important fundamental identities that can be easily proven by the definition of sine theta, cos theta, and tan theta, as well as cotan theta. So we're going to start off saying that we know tan theta is y over x, okay? And we know that if we divide top and bottom by the same thing, we haven't changed our fraction, so we're going to divide top and bottom by r, which means the top would look like y over r, y divided by r, or y over r, and the bottom can be written as x over r. But then we know from last week and from our diagram here that y over r is the sine of theta and x over r is the cos of theta. So we can rewrite y over r as the sine of theta and x over r as the cos of theta. So here's a very important identity. Tan is sine over cos. But since tan theta is sine over cos theta and cotan theta is the reciprocal, then we can just flip sine over cos upside down and get that the cotangent of theta must be cos theta over sine theta. So those are all the fundamental identities, and you have a sheet to print out that has the fundamental identities on it. So we're just going to look at that for a second. So these are our fundamental identities. So again, these 6 are our reciprocal identities. And these are the identities that Mr. Salawiga will want you to know next year in advanced functions. So tan and cotan are, tan being sine over cos and cotan being cos over sine are very important identities as well. They allow you to change, well, you'll see, but they allow you to change something from being in terms of tan to being in terms of sine and cos, which is very important. And then we have our 3 Pythagorean identities, this one, and this one. So what are these 2? This is just to show you that if we start with sine squared theta plus cos squared theta equals 1, if I want to get sine squared theta by itself, all I would do is subtract cos squared theta on both sides. Since this is an identity that's been proven, that's always true, any way we rearrange it, that will also be true. So this one's also true. And then in the same way, we could have decided to get cos squared theta by itself by subtracting sine squared theta on both sides. Sorry. And then it's another version. Okay, so these two are just different versions of the most famous Pythagorean identity there. Okay, and similarly, you could solve this one for tan squared, or you could solve this one for cotan squared, and you'd have a different version as well. Okay. All right, so those are your fundamental identities. So what do we do with the fundamental identities? Well, we use them to prove. When I was in school, we would be given a trig identity, and we'd be asked to prove whether this was another identity or not. Okay, so to prove an identity means to show that the left side and right side are actually equivalent expressions. They're actually just different ways of writing the same thing. In order to show this, the left side and right side should be dealt with separately, and some of the strategies below may prove helpful. Okay, so here's some strategies. Start with the more complicated side. Use known identities to rewrite the two sides so that they're in terms of the same trig functions. An important bridge identity. So for instance, if one side had tan in it and the other side only had sine or cos, this bridge identity that tan is sine theta over cos theta can be really useful. Use algebraic operations such as expanding, which is multiplying, factoring, simplifying, or finding a common denominator. And once you have the exact same expression on both sides, you've proven the identity and are required to write a therefore statement. Okay, so start off the pretty straightforward one, and we'll get a little bit more complicated. Okay, so how do we start these? So what we're trying to do is prove that cotan theta times sine theta is actually equal to cosine theta, that these two sides are equal, which means that it's an identity. It's true for all values of theta. So we're trying to prove it. We're not assuming it's true. So what we do is we're going to make a left side, right side chart. So to prove it, again, we can't assume that it's equal. We have to prove that they're equal. Okay, so we can't move things from side to side. We have to use each side on its own and try to make them equal each other. So our left side is cotan theta times sine theta, and our right side is cos theta. So starting with the more complicated side, cotan theta times sine theta looks more complicated than just plain cos theta. So we're going to start with the left side this time. And within a side, we don't want an equal sign in the middle because that would be assuming they were equal, and we're trying to prove it. But within a side, we're going to say that whatever we write next on the left side is going to be equivalent to cotan theta times sine theta. Now cotan theta, we have a bridging identity we can use there. So cotan theta is the same as cos theta over sine theta. That's an identity that we know for sure, we've proven. So we could rewrite cotan theta as cos theta divided by sine theta. So we've replaced cotan theta with cos theta cos theta divided by sine theta. And then we're still multiplying by sine theta. So we've kind of got like a fraction times a whole. So we know how to multiply those top by top. So cos theta times sine theta is just written cos theta sine theta. And then sine theta times 1 is just written sine theta. Now we have cos theta being multiplied by sine theta and being divided by sine theta. So the sine thetas divide to give you 1. So on this side, you're left with cos theta, which just happens to be what's on the right side. So when you have got it so your left side and right side match, we do a double underline. And now we've proven that the cotangent theta times sine theta is actually equal to cos theta, that it actually is an identity. So we say, therefore, left side equals right side, therefore proven. Okay, notice I don't have equal signs down the middle. I made a T-chart. I recopied the left side, recopied the right side, and then I used the more complicated sign and an identity that I already knew was true, which was that cotan theta was cos theta over sine theta. Then I multiplied and divided all within this side to create equivalent expressions, and then it turned out that the left side and right side were equal. When I was in high school, they would give you ones that didn't work, and you could spend hours and hours and hours trying to get them to work, and then finally you would convince yourself they weren't. But nowadays, they're all gonna be true, so you just have to find out how to prove that they're true using proper mathematical strategies. Okay, so here's our second one. So we're gonna set it up the same way, the T-chart. Left side, LS, right side, RS, recopy, cos theta, sec theta, sine squared theta plus cos squared theta. So this one's kind of a toss-up on which side's more complicated. Maybe I'll start with the left side because I see on the right side has sine and cos, and I kind of feel like sine and cos are building blocks. So if one side's got sine and cos and the other one has something other than a sine or a cos, there's lots of identities from this sheet that you can use. So I see a sec on the left side, and I can see that I can rewrite sec theta as 1 over cos theta. So I think that I will do that. So I'm going to leave my cos theta, because sine and cos are like my building blocks. But I'm going to replace secant theta with 1 over cos theta. And then I can use that strategy. Remember, these are really the same thing, just different ways of writing it. And now I can multiply. So top by top, bottom by bottom. And then that turns out to be 1. And then sine squared theta plus cos squared theta also equals 1, because that's the most famous trig identity. We proved that. It's our most famous Pythagorean identity. So we've proven that both sides are equivalent to 1. So now both sides match, so double underline. Therefore, left side equals right side. Therefore, proven. And again, there's no equal signs down the middle, just within a side itself. And we've worked on each side until we've got them to match. Then we've proven, once we've got each side to match, we've proven that the beginning cos theta sec theta equals sine squared theta plus cos squared theta is an identity. It's true for all values of theta. Okay. So this one, I'm going to put my T a little bit over to this so I have more room on the left side than the right side, because I can see that the right side looks like it's done. There's nothing I feel like I could do. It's just sine theta. So I'm going to focus my work on the left side here. And I notice again that the right side is made out of one of the building blocks. So I think about sine theta and cos theta as kind of being the building blocks. So then I would want to look at my list of identities and see if there's a way that I could write tan theta that's in terms of sine or cos or both. And we proved earlier that, tan theta can be written as sine theta over cos theta. So I'm going to replace tan theta with sine theta over cos theta. So this and this are equivalent. Now I want to replace sec theta with something that's equivalent to it. So if you look back on your identity sheet, sec theta, I can rewrite as 1 over cos theta by using a reciprocal identity. So now I've changed sec theta so it's into the building block cos. So I'm changing sec theta to 1 over cos theta. So these sec theta and 1 over cos theta are equivalent. Okay, so there's my equal sign. So now I'm going to go down another step. So now I've got a fraction divided by a fraction. So I know the rule for dividing fractions is you keep the first fraction the same and multiply by the reciprocal of the second one. So I'm going to flip that upside down. And then equal sign, so I'm going to multiply top by top, bottom by bottom. And then you can see that the cos thetas are going to divide out, multiplying and dividing by cos theta. And then I'm just left with sine theta, which is what's on the right side. So now I've got the two sides to match. Therefore, left side equals right side, therefore proven. Okay, D. So this time I'm going to leave more room on the right side because it looks more complicated. And definitely the right side looks more complicated, so I would start with that. The left side's in terms of sine, it's sine squared theta, but it's in terms of the building blocks, sine and cos. And cos is fine, sine is fine. Let's see if there's a way to rewrite cotan, so it's in terms of sine and or cos or both. And we can. Cotan theta is cos theta over sine theta. So that would be my second step. So I'm going to leave the numerator the same here, cos theta, sine theta. And then I'm going to rewrite cotan theta as cos theta over sine theta. So that cotan theta is the same as cos theta over sine theta. So now I've got kind of like a whole divided by a fraction. So we know that to divide by a fraction, you multiply by the reciprocal. So the reciprocal of cos theta over sine theta is sine theta over cos theta, and this is over 1. Multiply the numerators together, so I have cos theta times sine theta times sine theta. So sine theta times sine theta is actually sine theta squared, but we write that as sine squared theta. And then 1 times cos theta is cos theta. And our cos thetas divide out. So we're left with sine squared theta, which is what we have on the left side. Again, notice that my equal signs aren't in the middle. They're just to the right side, showing that each next step is logically equivalent to the step before it. So we've proven that the left side and right side are equal. So again, what did we prove? We proved that sine squared theta is just another way of writing cos theta times sine theta divided by cotan theta. Trig identities are kind of like puzzles. Okay, you want to start with something where they look totally different and then using math prove that they're actually the same, which is what we did here. Okay. All right, next one. Cosecant theta times secant theta is equal to cotan theta plus tan theta. Okay, so we'll start off with our left side, right side chart. Okay, so this one, the sides don't look all that complex, but we've got one side that's in terms of cosecant and secant, and the other one's in terms of cotan and tangent. The bridge that we'll be able to do then is to try to write them both in terms of sine and cos, or both. Okay, so break them down into the building blocks. So using our sheet of identities, if we just start on the left side, we can see that we could write cosecant as 1 over sine and secant as 1 over cos. So let's go ahead and do that. So we can write cosecant as 1 over sine theta and secant theta as 1 over cos theta. So again, these are equivalent and these are equivalent. So we still have equivalent expressions. But now instead of multiplying these ratios, we're now multiplying these fractions, if you want to think about it that way. So 1 times 1 is 1. Sine theta times cos theta is sine theta cos theta. And now I would say this side's kind of into its building blocks. The top is a 1. The bottom is sine theta times cos theta. So I would move over to the right side now because I don't think there's more I could do on this side. So then back to my identity sheet, cotan theta can be written as cos over sine, and tan theta can be written as sine over cos. So we can change that. So cotan theta is cos theta over sine theta, and tan theta is sine theta over cos theta. So again, these are equivalent, and these are equivalent. So we still have equality on the right side. So now what's actually happening here now is we're adding fractions together. So to add fractions, that's where you need a common denominator. So the common denominator, if one denominator is sine theta and the other is cos theta, the common denominator will be sine theta cos theta. Now, to get from the denominator sine theta to the denominator sine theta cos theta, I had to multiply the bottom by cos theta, which means I have to multiply the top by cos theta. Cos theta times cos theta is cos theta squared, or cos squared theta. And to get from the denominator cos theta to the denominator sine theta cos theta, I would have had to multiply the bottom by sine. So I have to multiply the top by sine, giving me sine squared theta. Now that I have a common denominator, I just need to write it once. So the common denominator is sine theta cos theta. And then I want to show that I'm adding the numerators, adding them over the common denominator. So there's no reducing I can do here because this plus sign is blocking me from that. If this was cos squared times sine squared, then yes, I could divide out a cos and a sine, but I can't. But the most famous identity that we should know is that sine squared theta plus cos squared theta, or cos squared theta plus sine squared theta, is equal to 1. So I can replace the numerator, cos squared theta plus sine squared theta, with 1 over sine theta cos theta. And now we have shown that the left side and right side are equal. So therefore, the left side equals the right side. Therefore, proven. Okay, next question. So I got right to the edge of the page here. Left side, right side. So they both look complicated, but I would say maybe the left side looks more complicated. So let's try to go back to our building blocks again of sine and cos if we can. It may take a few steps. Cosecant, if we look onto our sheet of fundamental identities, cosecant can be written as 1 over sine. Sec squared theta minus 1. Okay, so a little hint is whenever you notice a squared and a 1 together, you should be thinking about the Pythagorean, the 3 Pythagorean identities that we developed. So let's see if one of those, I wrote them down here, they're also on our fundamental sheet, but there is one that involves a sec squared and a 1, okay? So if this was our identity, I'll go to my sheet of identities here. We have 1 plus tan squared equals sec squared. And then remember when we were changing around the sine squared theta plus cos squared theta equals 1 identity to give us the other 2? We can do something similar here. So if we start with the identity that 1 plus tan squared theta equals sec squared theta, but we want to know what sec squared theta minus 1 is, we could subtract 1 from both sides, and we get that tan squared theta is sec squared theta minus 1, which means if I have sec squared theta minus 1, I could rewrite it as tan squared theta. So we're going to do that. So we just showed that if we had sec squared theta minus 1, we could rewrite it as tan squared theta. All right, so if we multiply the tops together, we get tan squared theta, and the bottoms together, we get sine theta. So if we look at both sides, they do not match yet, okay? So what's another way of writing tan? So it's in terms of our building blocks, sine and cos. Well, again, we've got this identity here. Tan is sine over cos. If we square this side, we should be able to square this side. So that should lead us to see that tan squared theta is equal to sine squared theta over cos squared theta. So I can rewrite tan squared theta as sine squared theta over cos squared theta. That's over sine theta. So this tan squared is the same as sine squared over cos squared. And then we're dividing, which means multiplying by the reciprocal. So sine squared theta over cos squared theta times 1 over sine theta. multiply the tops together and the bottoms together. And this sine theta on the bottom divides out with one of the two sines multiplying together on the top, so that gets rid of the squared. So we're left with sine theta over cos squared theta. So now we've got the left side in terms of the building blocks, sine and cos. So let's do the same thing with the right side and hope that they become the same. So tan theta we know we can write as sine theta over cos theta. So I just rewrote tan as sine over cos, but that's still being divided by cos theta. And we know that divide is multiplying by the reciprocal, so sine theta over cos theta times the reciprocal of cos theta, which is 1 over cos theta. Multiply the numerators together, denominators together, and we come up with the sine theta over cos squared theta again. So we've shown that both sides are the same. Okay, another one. Looks like the left side is going to be more complicated than the right side. So if I was trying to decide what was the more complicated side, I would see on the right side, there really isn't anything I can do. It's in terms of sine and cos. They're multiplying in the bottom. So I would leave the right side and move on, starting on the left side instead. And I know that I could rewrite tan theta as sine theta over cos theta. I know from my identity sheet that 1 over tan theta is the same as cotan theta. And I know from my identity sheet that cotan theta is the same as cos theta over sine theta. So now I have two fractions to add together, which we've done before in a previous example. So we need a common denominator. The denominators are cos theta and sine theta. So the common denominator is going to be cos theta sine theta. And then what do we have to multiply cos theta by to get cos theta sine theta? You need to multiply by sine theta. So we're going to multiply the top by sine theta, giving us sine squared theta. What do we multiply sine by to get cos times sine? Cos. So we want to multiply the numerator here by cos theta, giving us cos squared theta. Now we want to add the numerators over the common denominator. And then again, there's a plus in the middle, so we can't do any dividing out. But the top again turns out to be a version of our most famous identity, sine squared theta plus cos squared theta. Sine squared theta plus cos squared theta equals 1. So I can replace the numerator with 1. And the denominator is cos theta times sine theta, but if I look on the right side, I've got sine theta times cos theta. It doesn't matter what order you multiply two things in, so I can just write this denominator as sine theta cos theta. And they're the same. So indicate that with your double underline. So we can say, therefore, the left side equals the right side. Therefore, proven. Okay, H. So looking at the left side and right side, the right side, it's building block cos and 1. Here, this one looks too pretty simplified, but there's got to be a way that we can show that they're the same. So on the right side, there's no sine. On the left side, there is. So is there a way that we can write sine so it's in terms of just cosine? Well, not sine, but there is a way of writing sine squared, so it's in terms of cos squared. And that's using our most famous identity, sine squared plus cos squared equals 1. So starting with the sine squared plus cos squared equals 1 identity, if we want to get sine squared by itself, we'd subtract cos squared on both sides, which is shown here. That sine squared theta is the same as 1 minus cos squared theta. So we're going to do that. So we're going to rewrite sine squared theta as 1 minus cos squared theta. Okay, so what we did is we rewrote sine squared theta as 1 minus cos squared theta. And again, it's tempting to think that we could do some kind of canceling here, but we can't because of the subtraction sign. Okay? But 1 minus cos squared theta, we can think of it as being similar to having 1 minus x squared. 1 minus something squared, or a difference of squares. And we know that 1 minus x squared would factor using a difference of squares to give us 1 minus x times 1 plus x. In the same way, 1 minus cos squared theta will factor to give us 1 minus cos theta times 1 plus cos theta. And now we've got two factors that are multiplying each other in the numerator and another binomial factor in the denominator. And these two happen to be exactly the same factors, so we can simplify them like we simplified rational expressions, divide those out. And now we're left with 1 plus cos theta, which is what we have on the right side. So that was our first one where we used factoring to help us prove the identity was true. So we've proven the left side equals the right side. And we've proven that identity. So we had to use the most famous identity, sine squared plus cos squared equals 1, to get sine squared by itself and rewrite it as 1 minus cos squared. Then we had to use the fact that 1 minus cos squared was set up like a difference of squares with the 1 first. Factor it the same way we would factor 1 minus x squared, only instead of x we have cos theta. And then we had the same factors in the top and the bottom that we could divide out that left us with 1 plus cos theta, which is what was on the right side. So factoring helped us there. So far strategies that have helped us if we look backwards: factoring, finding a common denominator, and in these cases we've been using identities as well. Just operations like multiplying and dividing fractions have been really important, along with identities. Multiplying, dividing fractions, adding fractions, and factoring have been our strategy so far, as well as really using all these fundamental trig identities and playing around with them and trying to get both sides so that they're in terms of just sine and cos, or one or the other. our common strategies. Okay, so here I'm gonna do like, definitely the left side is way more complex and it looks very intimidating actually. But there's a little clue in the question, and that is that the denominator of the left side is in factored form, cos theta times 1 plus sine theta. So when you see that the bottom's in factored form, you would want to check and see if there's anything you could factor, or you could put the top into a factored form. So sine theta plus sine squared theta has a common factor of sine theta. So think about, if I want to common factor out sine theta, it's like you want to mentally divide each of these chunks in the numerator by sine theta. So common factoring out sine theta divided by sine theta is 1. Sine squared theta divided by sine theta is sine theta. And over cos theta times 1 plus sine theta. And then all of a sudden, it becomes really clear that these 1 plus sine thetas can divide out. So we're just left with sine theta over cos theta. And then if we look on the right side, tan theta, the bridging identity is that tan theta is equal to sine theta over cos theta. It's one we've been using a lot of. So now we've got the left side and right side equaling. So something that looked really, really challenging was actually easier to prove than some of the ones that looked less difficult at the beginning. And our clue in the question was that the denominator here was already in factored form, so that would lead us to look and see if the top could be factored. Okay, J, this is our last one for today. Okay, so this one looks very complicated. Both sides look fairly complex for what we've been looking at so far. The left side looks more tricky. When they look like really complicated like this, we're hoping that they factor somehow. So cos squared minus sine squared, it's like a difference of squares again. It can be thought of as having x squared minus y squared, which factors to give you x plus y times x minus y. So if we apply that pattern to cos squared theta minus sine squared theta, we're going to get cos theta minus sine theta times cos theta plus sine theta. Okay, so cos squared minus sine squared can be factored to give us cos minus sine times cos plus sine. Over, in the denominator, I've got my two chunks here, cos squared theta and sine theta cos theta. They have cos theta in common. So I can common factor out cos theta and divide this first. Cos squared theta by cos theta gives me cos theta plus sine theta cos theta divided by cos theta gives me sine theta. And then I have a binomial bracket cos theta plus sine theta in the denominator and in the numerator, so they can cancel out, which gives me cos theta minus sine theta over cos theta. Okay, so we're going to use a strategy that we haven't used yet. Here we have a common denominator of cos theta. What we're actually going to do instead is break it up into two fractions subtracting. So cos theta minus sine theta all over cos theta means exactly the same thing as cos theta over cos theta minus sine theta over cos theta. We're used to going this way, where we get our common denominator and then we subtract the numerators over the common denominator, but we're going to do a little something different. We're going this way instead. So, and the reason is because cos theta divided by cos theta is 1, and then minus sine theta over cos theta. We could either leave it as sine theta over cos theta, but we also know that that's tan theta. Now let's come onto this side and use that similar strategy. We've got the common denominator of cotan theta. So let's write it as cotan theta over cotan theta minus 1 over cotan theta. So something divided by itself is 1. And then 1 over cotan theta is one of our reciprocal identities. So 1 over cotan theta can be written as tan theta. So that same strategy of taking something that has a common denominator and splitting it up the numerators into each little part over that common denominator and then reducing each part separately helped us to get the sides to match. So that's a technique we don't use very often, but is really helpful in trig identities. So again, just involves fractions and looking at them differently. So our success criteria for today's lesson were that we can rewrite one or both sides of a trig identity so that both sides are in terms of the same trig functions. We use that a ton of times trying to write things in terms of sine and cos most often. We can use strategies such as expanding, factoring, simplifying, and the types of factoring we used were difference of squares and common factoring, simplifying, finding a common denominator, okay, and we also dealt with fractions multiplying, dividing fractions, adding fractions, subtracting fractions, and all of these were used to find an equivalent way of rewriting a side. We use the chart format to organize your proof and help to work on one side at a time, and showing that logical equivalence on each side, so our equal signs are within a side, not in the middle. We make that chart. And once we've shown both sides are the same, they're actually equivalent expressions, you conclude your proof with therefore left side equals right side, therefore proven. All right, that's Identities, Day 1.